Hello and welcome to part 3 of the Introduction to Differentiation series. In this video, we're going to be looking at some special functions differentiations. These special functions are functions just like natural log or maybe some trigonometric functions or the inverse of trigonometric functions. And these have special types of differentiation that we will look at. And at the end of the video, we're going to practice some questions as well that combines these new ideas with the previous video for the product rule, quotient rule, and chain rule, which I really advise you to go and check out first. I will leave it on the top right corner for you to check it out and then come and continue this video. Okay, so let's start by saying what is the differentiation of e to the power of x. Simply, e to the power of x is basically the differentiation of e to the power of x is basically itself. It's e to the power of x. This is the simplest differentiation ever. But, however, if we have e to the power of a function in terms of x, then chain rule applies. And we talked about chain rule in the previous video. So let's take an example where if we have d by dx of 3x squared. So again, what we do is we differentiate the big function, which is e to the power of x. Okay, so it's basically itself. However, our x here is now 3x squared. So itself is going to be e to the power of 3x squared. That's the differentiation. And then we multiply by the differentiation of the small function, or what's inside. So the differentiation of 3x squared is going to be coefficient times power, which is 2 times 3, which is 6. X, and then we reduce the power by 1, so 2 minus 1 is basically 1. So our answer is going to be 6x times e to the power of 3x squared. So basically, you can say that d by dx of e to the power of u, where u is a function in terms of x, is going to equal e to the power of u multiplying the differentiation of this u function, or we can call it as u dash. Okay, so let's continue. Let's take an example where the next idea, which is the differentiation of the natural log of x. So the differentiation of the natural log of x is basically 1 over x. Again, chain rule applies. So let's say we have an example of d by dx of ln, let's say 3x plus 4. Again, we're going to differentiate the big function, considering this 3x plus 4 as just a simple x. So it's going to be 1 over, instead of x, it's going to be whatever is inside. So it's going to be 1 over 3x plus 4. And then we multiply the whole thing by the differentiation of what's inside. The differentiation of 3x plus 4 is basically 3. So my answer is going to be 3 over 3x plus 4. So the chain rule will always apply to all of these new special differentiations that we're taking. Okay. Let's continue. Let's say we have the differentiation d by dx of a to the power of x. This is basically going to equal a to the power of x multiplying ln of a. And I would like to give you quickly what the proof for this differentiation. So I can rewrite a to the power of x as e to the power of ln a to the power of x. Why? Because I know that e to the power of ln anything is basically equal to that thing. So basically this part, e to the power of ln a, so e to the power of ln a is equal to a. And I know that I want the differentiation of a to the power of x, so this part is a, I'm going to raise it to the power of x. So basically, this is exactly the same as a to the power of x. Then I can rewrite this as e to the power of x times ln ln of a. Why? Because I know from the indices or exponent rules, I know that a to the power of b all to the power of c is going to equal a to the power of b times c. So here, this is our b, this is our c, so these two are equal. So let's now try to find the differentiation of this. So if this is y, then dy by dx, or the differentiation, is going to be the same. We know that the differentiation of e power anything is basically e to the power of that same thing, and then we multiply by the derivative of the small function. So what is the derivative of x ln a? Ln a is a constant, similar to the constant 2 or like 3.5 or whatever. Ln a is just a constant, and we know that any constant multiplying x, its derivative is basically that constant. So 2. So differentiation of x ln a is nothing but ln of a. It's basically that constant. Okay, so till now we have this here. So we can rewrite this as e to the power of ln a all to the power of x times ln of a. And I know that e to the power of ln a is the same as a, basically. So this is going to be a, and then I have to the power of x multiplying ln a, which is the same as this part over here. Again, if my a or if my x is not just simply an x, it's just a function. Let's say we want to get the differentiation d by dx of a to the power of let's say 2x squared plus x. Okay, so differentiation of a to the power of u, okay, where u is a function of x, is supposed to equal a to the power of u times u dash, or the differentiation of the small function, which is u, multiplying ln of a. Let's try to do the same thing to see if we will reach that thing. So a to the power of 2x squared plus x, I can rewrite it similarly to what I did in the first example. I can rewrite it as e to the power of ln a. This part is basically equal to this a, and then everything to the power of 2x squared plus x, and then again I can multiply this power to this power here, so it's going to equal e power 2x squared plus x multiplying ln of a. And then let me get the derivative of this. If this is y, let me get dy by dx. So again, the differentiation of e power anything is basically e power the same thing, 2x squared plus x ln a, and then I multiply by the derivative of this small function. So I know that this small function, if I distribute this ln a, is going to be ln a multiply 2x squared plus ln a multiply x. So basically differentiating this, ln a is a constant, so basically I can differentiate this as, this is going to be 4x times ln a, plus this is basically anything constant multiplying x, its derivative is basically that constant. So basically I can take ln a as common, so it's going to be 4x plus 1. This is basically the differentiation of what is inside, and I'm going to multiply by that over here. So ln a times 4x plus 1. So again, I can rewrite this part as e to the power of ln of a all to the power of 2x squared plus x, and then multiply ln of a 4x plus 1. So basically, this part, we know that this is equivalent to a power 2x squared plus x, and then multiplying, let's say 4x plus 1 first, okay, and then multiplying ln of a, and this is basically the same as what I told you. If u equals 2x squared plus x, then this is exactly the same as a power u times u dash. This is a differentiation of u dash times ln of a, which is exactly the same as what we wrote over here. So basically the differentiation of a power anything is a power that thing times the differentiation of that thing times ln of a. Okay, let's continue from here. Going over to the trigonometric functions, okay, I know that the differentiation of sine of x is basically cosine of x, and the differentiation of cosine of x is negative sine of x. The differentiation of tan of x is going to equal secant squared of x. The differentiation of cotan of x is going to equal negative cosecant squared of x. And the differentiation of secant x is going to equal secant x times tan x. These are similar to the identities of trig functions. They all have proofs, and if you want the proofs, you can send me down below on the comments and I'll do a video for the proofs. However, these are best memorized as they are similar to the identities of the trig functions. And by the way, I've done a video on my YouTube channel for the trig identities, and I'd encourage you to go check it out. I'll leave it on the top right hand corner right now. Okay, so continuing from here, our final part is when we have d by dx of inverse sine of x. This is basically 1 over square root of 1 minus x squared. And the differentiation of the inverse of cosine of x is going to equal negative. It's the same exact thing, however, it's just multiplied by negative 1 square root of 1 minus x squared. When I have the differentiation of inverse of tan of x, this is going to give me basically 1 over 1 plus x squared. And these are basically the trigonometric differentiations that you will need to know. We have one more differentiation we need to look at, which is basically differentiation of log to the base a of x. This is basically equal to 1 over x ln a. And this is super similar to differentiation of ln of x, which we talked about, because ln of x is nothing but log to the base of e x. So we know that ln of x equals, the differentiation of ln of x is 1 over x, and by applying this rule, we should also reach 1 over x, because if we want to differentiate this using this rule, is basically going to be dy by dx is going to be 1 over x times ln of a, and a here is e, and I know that ln of e is basically 1, so it's going to equal 1 over x. So these is basically how we got these. These are 80% of differentiation done, and most of the things that you will need to do. So let's take some examples to combine what we know now with what we've done in the previous videos, and to provide you with more understanding for everything. So let's say we have y equals sine 2x. I know that y dash, or basically, because dy by dx, I can rewrite it as y dash. So y dash is going to be, I know that the differentiation of sine of x is cosine of x. So I have a sine of 2x, so it's going to be cosine of 2x multiplying the differentiation of what's inside, which is basically 2. So the answer is going to be nothing but 2 cosine 2x. Let's take another example. Let's say we have y equals x squared sine of x. This is similar to the product rule, and from the previous video, we know that for the product rule, it's basically differentiation of the first, this function, and this function. This is the first function, this is the second function. So it's differentiation of the first, so it's going to be 2. Let's just erase these so we're not confused. So it's going to be 2x, and then multiplying the second function, and adding to that the first function without any differentiation, and then the differentiation of the second function, and we know that differentiation of sine x is cosine x. So this is going to be my answer. Let's take another example. Let's say we have an example of y equals x squared over tan of x. So this is basically the quotient rule. So y dash, or dy by dx, is going to equal, we know that the quotient rule says it's the differentiation of the numerator function, so it's 2x, multiplying the denominator function, and then subtracting the numerator function multiplying the differentiation of the denominator function. And what is the differentiation of tan x? We know that it is secant squared of x. And all of that over tan squared of x, or over the denominator function squared. So this is basically going to be my answer. Right. Let's take more examples. Let's say we have y equals e to the power of x cubed. So I know that y dash of e to the power of anything is basically e to the power of that thing, so x cubed, and multiplying the differentiation of what is over here. So the differentiation of x cubed is basically 3x squared. So it's equal to 3x squared multiply e to the power of x cubed. And that is my answer. Let's take question 5, which says that y equals x ln of x, and I need to get y dash. This is again the product rule. So we know the product rule is basically the first differentiated, so the differentiation of x is basically 1. So I have a 1 times the second function, and then adding to that the first function multiplying the differentiation of the second function, and we know that differentiation of ln of x is 1 over x. So here x and x cancel, I have a 1, so my answer is going to be 1 times ln x, which is ln x plus 1. Let's take another example, saying y equals negative 4 e power negative 4 of x over 4 e to the power of 4x. I know that I can have this 1 over 4 outside, so I will leave it as 1 over 4. And then I can have this e power negative 4x. And then multiplying to that, I know that when this e to the power of 4 of x is in the denominator, if I want it in the numerator, I need to multiply the power by minus 1. So it's going to be like this. So it's going to be 1 over 4. And I know that when I have the same base, I can basically add the power. So it's going to be equal to e power negative 4x plus negative 4x, which is equal to 1 over 4 e power negative 8x. All of that we're rewriting. We didn't start getting our differentiation. So if you want our y dash, it's basically going to be equal 1 over 4. And then we know e power negative 8x is going to be, the differentiation of that is e to the power of negative 8x multiply what is this part over here, the differentiation of that. So the differentiation of negative 8x is basically negative 8. So I will have a negative 8 divide 4 is basically a negative 2 e to the power of negative 8x, or you can rewrite it as negative 2 over e to the power of 8x, because when this goes to the denominator, I multiply it by negative 1, so it becomes a positive 8x. Continuing from here, let's take a couple more examples. Let's say we have example number 7, y equals ln of 1 over e power x. So let's rewrite that to a differentiable form. So let's write it as ln of e power negative x. Okay. Differentiation of that is going to be, I know that the differentiation of ln of x is basically 1 over x. So the differentiation of ln of e power negative x is 1 over e power negative x, and then multiplying the differentiation of what is inside. So what's the differentiation of e power negative x? It's basically e power negative x multiplying the differentiation of what's inside. So multiplying the differentiation of negative x, which is basically negative 1. So this is equal to negative e power negative x. And here we use the chain rule twice. So again, we need to multiply this by the differentiation of e power negative x, which is this. So multiply negative e power negative x. So e power negative x and e power negative x, they can cancel out. I will have a 1 times negative 1, which is going to give me an answer of negative 1 at the end. Let's take one more final example. Let's say we have y equals sine x cosine x tan x, and I need y dash. Again, I can use the trigonometric identities to help me. I know that tan x is equal to sine x over cosine x. So let's rewrite that as sine x cosine x, and instead of tan x, I'm going to write sine x over cosine x. And now I can find that this cosine x and this cosine x will cancel, and I'll have a sine x times sine x, which is basically sine x squared, or it's written as, this is equivalent to sine squared of x. These two are the same. So y dash of that is basically the differentiation of this. Again, I will use the chain rule. So this is something squared. So I know that I will, to use my square chain rule, I will do power times coefficient. So 2 times 1 is 2. Then sine of x and reduce the power by 1. So 2 minus 1 is basically 1, or we don't need to write it. And then multiply by the differentiation of what is inside. This is again application of the chain rule. Differentiation of sine x is basically cosine x. So my answer is 2 sine x cosine x. So basically, what we've covered today is most of the important special functions that you will need to know their integration, their special integrations, where they are mostly memorized, okay? And from here, I believe in the next video, we are ready to start doing the applications of differentiation and how will it help us, because now we know how to differentiate most of the equations that can come across. Please don't forget to like and subscribe. Don't forget to turn on your notifications. If you have any suggestions or any topics or any questions, leave them in the comments down below. Always happy to help, and thank you for watching.